Electricity has an important place in modern society. It is a controllable and convenient forms of energy for a variety of uses in homes, schools, hospitals, industries, and so on. Electricity has a very important role in our daily life. Almost everything of our modern conveniences and needs are electrically powered. Our homes are bright even after sunset. You must know that lights in our homes work on electricity. However, they're not the only ones that use electricity. Our televisions, air conditioners, water heaters, fans, and so on also need electricity to function. Even small flashlights also work on electricity. Imagine a life without electricity in the world today. Large machines in industries are worked with the help of electricity. Today the vast and majority of medical machinery in a hospital works with the help of electricity. And you are using electricity right now to see this video through your phone or computer. So electricity has huge impact in our lives, which makes our life comfortable, convenient, and easy. In this chapter, we will try to understand what is electricity, how does electricity flow in an electric circuit, what is current, what are the factors that controls or regulate the current through an electric circuit. We shall attempt to answer such questions. We shall also discuss the heating effect of electric current and its applications. Electric current and circuit. First, let us understand what is current. So current is basically a flow or a stream of a particular object or thing in a desired direction is called current. For example, if we are making a flow of air in a particular direction, it is called as air current. Another example, water current. River flows in a particular direction and it is called as water current. Any objects that flow in a particular direction are called that particular object current. Let us take one more example of tennis ball machine. So tennis ball throws a ball in a desired direction is called tennis ball current. Similarly, if electric charge flows through a conductor through metallic wire, it is called as electric current. Let us take a torch. Now, in a torch, we know that the cells or a battery, when placed in proper order, it provides flow of charges or an electric current through the torch bulb to glow. We have also seen that the torch gives light only when it's switched on. So, what is a switch and what does it do? A switch is a conducting device used to make or break a connection in circuit, so you can either turn on or turn off. What is electric circuit? A continuous and closed path of an electric current is called an electric circuit. If the circuit is broke or the switch is turned off, the current stops flowing and bulb does not glow. Consider a simple circuit consists of battery or a cell, bulb, connecting wire, and switch in series with ammeter to measure the current. How do we express electric current? Electric current is expressed by the amount of charge flowing through a particular area in unit time. In other words, it is rate of flow of electric charge. What is the direction of electric current? In circuits using metallic wires, electrons constitute the flow of charges. However, electrons were not known at the time when the phenomenon of electricity was first observed. So, electric current was considered to be the flow of positive charges, and the direction of flow of positive charges was taken to be the direction of electric current. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. Formula for current. If a net charge Q flows across any cross-section of a conductor in time t, then the current I through the cross-section is I equals to Q divided by T. The SI unit of electric charge is Coulomb C, which is equivalent to the charge contained in nearly 6 multiplied by 10 to the power of 18 electrons. The electric current is expressed by a unit called ampere. 1 ampere is constituted by the flow of 1 coulomb of charge per second. An instrument called ammeter measures the electric current in a circuit. It is always connected in series in a circuit through which the current is to be measured. Electric potential and potential difference. What is potential? The quantity determining the energy of mass in a gravitational field or of charge in an electric field is called potential. What makes an electric charge to flow? As we know, the charges in a copper wire does not flow by them. So what makes it flow? Let us consider the analogy, means comparison with water. Let us take 2 jars of same size and shape and fill the water in both the jars with equal quantity and place them on equal height, attached with a tube, and name them as jar A and B jar. If I want the water of jar B to flow into jar A, if we kept the jars in equal height, the water remains constant. When we increase the height of the jar B, then there are gravitational pressures on water in jar B, which make the water flow in jar A. Similarly, for the flow of charges in conducting metallic wire, the gravity, of course, has no role to play. The electrons move only if there is a difference of electric pressure, called the potential difference, along the conductor. This difference of potential may be produced by a battery consisting of one or more electric cells. So what is battery and how it works? Battery is a device prepared by metals and chemicals, which consist of chemical energy. This energy can be converted as electrical energy in a circuit. And this kind of batteries can be used in temporary electricity needs. Batteries can provide the pushing force that moves the electrons through the circuit. Turn on the switch and observe. We can see that the current starts to flow in the circuit. The chemical action within a battery cell or cell generates the potential difference across the terminals of the cell, even when there is no current is drawn from it. When the cell is connected to a conducting circuit element, the potential difference sets the charges in motion in the conductor and produces an electric current. In order to maintain the current in a given electric circuit, the cell has to use its chemical energy stored in it. We define the electric potential difference between 2 points in an electric circuit carrying some current as the work done to move a unit charge from one point to the other. Potential difference between 2 points equals to work done divided by charge. Therefore, V equals to W divided by Q. The SI unit of electric potential difference is volt. 1 volt is the potential difference between 2 points in a current-carrying conductor. When 1 joule of work is done to move a charge of 1 coulomb from one point to the other. Therefore, 1 volt equals to 1 joule divided by 1 coulomb. 1 volt equals to 1 J C to power of 1. The potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Factors on which the resistance of a conductor depends. In our previous section, we come to know that a resistor offers resistance or opposes to the flow of electrons. Let us study what are the factors which affect the resistance. Let us complete an electric circuit consisting of a cell, an ammeter, a nichrome wire of length L. Mark it has 1. Note the current in the ammeter. Replace the nichrome wire by another nichrome wire of same thickness but with 2 times increased length, that is 2L, and mark it as 2. Note the ammeter reading. Now replace the wire by a thicker nichrome wire of the same length L and mark it as 3. A thicker wire has a more width. Again, note down the current through the circuit. Now, instead of taking a nichrome wire, connect a copper wire and marked it as 4 in the circuit. Let the wire be of the same length and same area of cross section as that of the first nichrome wire. Note the value of the current. Notice the difference in the current. In all cases, we notice that the current depends on the length of the conductor and area of cross section, area of width, the wire which we used. It is observed that the ammeter reading decreases to 1/2 when the length of the wire is double. The ammeter reading is increased when a thicker wire of the same material and of the same length is used in the circuit. A change in ammeter reading is observed when a wire of different material of the same length and the same area of cross section, area of width, is used. On applying Ohm's law equations, V equals to IR to I equals to V by R, we observe that the resistance of the conductor depends 1 on its length, 2 on its area of cross-section, and 3 on the nature of its material. Precise measurements have shown that resistance of a uniform metallic conductor is directly proportional to its length, L, and inversely proportional to the area of cross-section, A. Area of width, that is, R proportional to L, and R proportional to 1 by A. After solving this equation, we get R proportional to L by A. Therefore, we can replace the equation to R equals to rho L by A. Here rho is a constant of proportionality and is called the electrical resistivity of the material of the conductor. The SI unit of resistivity is ohm meter. It is a characteristic property of the material. The metals and alloys have very low resistivity in the range of 10 power of minus 8 ohm meter to 10 power of minus 6 ohm meter. They are good conductors of electricity. Insulators like rubber and glass have resistivity of the order of 10 to the power of 12 to 10 to the power of 17 ohm meter. Both the resistance and resistivity of a material varies with temperature. Resistance of a system of resistors. In early sections, we learnt about some simple electric circuits. We have noticed how the current through a conductor depends upon its resistance and the potential difference across its ends. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combinations of resistors. There are two methods of joining the resistors together. In electric circuit in which three resistors having resistances R1, R2, and R3 respectively are joined end to end, one after the other, forming just one path and not multiple paths. Here the resistors are said to be connected in a series. The combination of resistors in which three resistors are connected together between the points of X and Y in multiple paths, and not one after the other, forming just one path. Here, the resistors are said to be connected in a parallel. Resistors in series. First, let us understand, by doing this activity, what happens to the value of current when a number of resistors are connected in a series. In a circuit, what would be their equivalent resistance? Let us try to understand these with the help of the following activities. Let us join three resistors R1, R2, and R3 of different values in series. Connect them with a battery, an ammeter, and a switch. Turn on switch and note the ammeter reading. Now, change the position of ammeter to anywhere in between the resistors. Note the ammeter reading each time. You will observe that the value of the current in the ammeter is the same irrespective of the reading of ammeter, from different positions from the circuit. So from this activity, we observe that the value of the current in the ammeter is the same, independent of its position in the electric circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit, or the same current through each resistor. Now, let's remove the ammeter between the resistors and try for something else. Insert a voltmeter across the ends X and Y of the series combination of 3 resistors. Turn on switch and note the voltmeter reading. It gives the potential difference across the series combination of resistors. Let it be V. Turn off the switch and disconnect the voltmeter. Now insert the voltmeter across the ends X and P of the first resistor. Turn on switch and measure the potential difference across the first resistor. Let it be V1. Similarly, measure the potential difference across the other 2 resistors separately. Let these values be V2 and V3 respectively. You will observe that the potential difference V is equal to the sum of potential differences V1, V2, and V3. That is the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual resistors. That is, V equals to V1 plus V2 plus V3. In the electric circuit, let I be the current through the circuit. The current through each resistor is also I. It is possible to replace the 3 resistors joined in series by an equivalent single resistor of resistance R, such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V equals to IR. On applying Ohm's law to the 3 resistors separately, we further have V1 equals to IR1, V2 equals to IR2, and V3 equals to IR3. Substitute the equation 12.12, 12.13a, 12.13b, and 12.13c with the equation 12.11. We get IR equals to IR1 plus IR2 plus IR3, or RS equals to R1 plus R2 plus R3. We can conclude that when several resistors are joined in series, the resistance of the combination RS equals the sum of their individual resistances R1, R2, R3, and is thus greater than any individual resistance. Resistors in parallel. When resistors are connected in parallel, what happens to the value of the voltage across each resistor and current through each of them? Let us try to understand these with the help of the following activities. Now, let us consider the arrangement of 3 resistors joined in parallel with a combination of cells or a battery. Make a parallel combination XY of 3 resistors, having resistances R1, R2, and R3, respectively. Connect it with a battery, switch, and an ammeter. Also connect a voltmeter in parallel with the combination of resistors. Turn on switch and note the ammeter reading. Let the current be I. Also take the voltmeter reading. It gives the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. Turn off the switch. Remove the ammeter and voltmeter from the circuit. Insert the ammeter in series and voltmeter in parallel with the resistor R1. Note the ammeter reading I1. Similarly, measure the currents through R2 and R3 by connecting ammeter and voltmeter. Let these be I2 and I3 respectively. What is the relationship between I1, I2, and I3? Let Rp be the equivalent resistance of the parallel combination of resistors. By applying Ohm's law to the parallel combination of resistors, we have I equals to V by Rp. On applying Ohm's law to each resistor, we have I1 equals to V by R1, I2 equals to V by R2, and I3 equals to V by R3. By substituting the equation from 12.16, 12.17a, 12.17b, and 12.17c, we get V by Rp equals to V by R1, V by R2, and V by R3. Or 1 by Rp equals to 1 by R1, 1 by R2, and 1 by R3. Thus, we may conclude that the reciprocal of the equivalent resistance of a group of resistances joined in parallel is equal to the sum of the reciprocals of the individual resistances. Conclusion. We have seen that in a series circuit, the current is constant throughout the electric circuit. Thus it is obviously impracticable to connect an electric bulb and an electric heater in series, because they need currents of widely different values to operate properly. Another major disadvantage of a series circuit is that, when one component fails, the circuit is broken and none of the components works. If you have used fairy lights to decorate buildings on festivals, on marriage celebrations, etc., you might have seen the electrician spending lot of time in trouble locating and replacing the dead bulb. Each has to be tested to find which has fused or gone. On the other hand, a parallel circuit divides the current through the electrical gadgets. The total resistance in a parallel circuit is decreased. This is helpful particularly when each gadget has different resistance and requires different current to operate properly. In this section, we will talk about the heating effect of electric current and the Joule's law of heating. Have you ever touched an electrical gadget after it has been working for a while? Take an example of an electric fan. It becomes warm if we used continuously for longer time. What causes this rise in temperature, and where does the heat come from? We know that the battery or a cell is the source of electrical energy for any circuit. All the electrical energy provided by the battery is not converted to useful work. As we have observed that when the current flows through a conductor or a gadget, this heating takes place in that conductor. A part of the source energy in maintaining the current may be consumed into useful work, like in rotating the blades of an electric fan. And some of the energy may be expended in heat to raise the temperature of gadget. When the current flows through a purely resistive circuit, that is, a configuration of resistors only connected to a battery, the source energy continually gets dissipated entirely in the form of heat. This is known as the heating effect of electric current. This effect is utilized in devices such as electric heater, electric iron, etc. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V. Let T be the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. Therefore, the source must supply energy equal to VQ in time t. Hence, the power input to the circuit by the source is P equals to V, Q divided by T equals to VI. Or the energy supplied to the circuit by the source in time t is P multiplied by T. That is VIT. What happens to this energy expended by the source? This energy gets dissipated in the resistor as heat. Thus, for a steady current I, the amount of heat H produced in time t is H equals to VIT. By applying Ohm's law, we get H equals to I square RT. This is known as Joule's law of heating. The law implies that heat produced in a resistor is first directly proportional to the square of current for a given resistance. Second, directly proportional to resistance for a given current. And third, directly proportional to the time for which the current flows through the resistor. In practical situations, when an electric appliance is connected to a known voltage source, the equation H equals to I square RT is used after calculating the current through it using the relation I equals to V by R. Practical applications of heating effect of electric current. The generation of heat in a conductor is an inevitable consequence of electric current. In many cases, it is undesirable as it converts useful electrical energy into heat. In electric circuits, the unavoidable heating can increase the temperature of the components and alter their properties. However, heating effect of electric current has many useful applications. The electric laundry iron, electric toaster, electric oven, electric kettle, and electric heater are some of the familiar devices based on Joule's law of heating. The electric heating is also used to produce light, as in an electric bulb. Here, the filament must retain as much of the heat generated as is possible, so that it gets very hot and emits light. It must not melt at such high temperature. A strong metal with high melting point, such as tungsten, the melting point 3380 degrees Celsius, is used for making bulb filaments. The filament should be thermally isolated as much as possible, using insulating support, etc. The bulbs are usually filled with chemically inactive nitrogen and argon gases to prolong the life of filament. Most of the power consumed by the filament appears as heat, but a small part of it is in the form of light radiated. Another common application of Joule's heating is the fuse, used in electric circuits. It protects circuits and appliances by stopping the flow of any unduly high electric current. The fuse is placed in series with the device. It consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example aluminum, copper, iron, lead, etc. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually encased in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are rated as 1A, 2A, 3A, 5A, 10A, etc. For an electric iron, which consumes 1 kilowatt electric power, when operated at 220 volts, a current of 1000 by 220A, that is 4.54A, will flow in the circuit. In this case, a 5A fuse must be used. Electric power. You have studied in your earlier class that the rate of doing work is power. This is also the rate of consumption of energy. The equation H equals to I square RT gives the rate at which electric energy is dissipated or consumed in an electric circuit. This is also termed as electric power. The power P is given by P equals to VI. It can also be written as V square divided by R or squared into R by applying the Ohm's law. P equals to I square R equals to V square by R. The SI unit of electric power is watt. It is the power consumed by a device that carries 1A of current when operated at a potential difference of 1 volt. Thus, 1 W equals to 1 volt multiplied by 1 ampere equals to 1 volt ampere. The unit watt is very small. Therefore, in actual practice we use a much larger unit called kilowatt. It is equal to 1000 watts. Since electrical energy is the product of power and time, the unit of electric energy is, therefore, watt-hour. 1 watt-hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt-hour, commonly known as unit. 1 kilowatt-hour equals to 1000 watt multiply by 3600 second equals to 3.6 multiply by 106 watt second equals to 3.6 multiply by 106 joule.